Okay, good morning, everyone. So let's continue with this chapter on potential energy. Let me just recap a little bit to refresh our memories. So we're talking about potential energy, which is the energy associated with the configuration of a system of objects. So the relationship between the change in potential energy is actually, it's kind of like it's got the opposite relation to the kinetic energy work theorem. So it's got a minus sign here, and so it's the negative of the work. So we looked at, let's see, what's wrong here? Just restart that then. Yeah. That one's back. Okay. All right. Hopefully it works again. So if you look at the kinetic energy and the potential energy, they sort of have the reverse relationship. So if you calculate the work here, the kinetic energy in this case goes down, but the potential energy goes up. And likewise when you release the spring. So we can kind of think maybe the analogy that might be useful to figure out why it's got this mutual negative sign is in terms of the bank account analogy. So if you look at the kinetic energy and there's some transfer, which is actually the work, then of course if you transfer some money from here to here, then this one goes up, this one goes down. So this is basically why there's a mutual negative sign relationship between those. And we also looked at conservative, non-conservative forces. So these are forces where if you go in a loop, it's asking basically whether the work to go in the forward direction is the same as the backward direction, and if it is, it's a conservative force. If it's not, it's a non-conservative force. And so basically the test to figure out if it's a conservative force is that if you go in a loop, same configuration, start and end, and if you look at the work done in the forward and the backward leg, if they're the same or in a closed path, so if the forward leg is positive, then the negative leg should be, the forward leg should be positive and the second leg should be negative, so that the total adds to 0. So if it satisfies that, then it's a conservative force, and then we could basically use this relation to figure out that it's actually also path independent. Here's some examples. And yeah, so I tried to explain this last time, maybe to confuse some of you, so maybe I'll just go through it quickly again. So basically, this is kind of the money analogy for the loop test. So what we're trying to do here is to go from this configuration, say $5, to $3, and then back to $5 again. So that's basically what we're trying to do in a loop test, right? So we have to end up at the same configuration that we started with. Now, if you could just transfer money, or in this, energy, between potential and kinetic energy, and you could do it without any loss, then you could, of course, get back to the initial point and the work would be, say, like $2 each way, right? So $5, you give $2 to this guy, and then $2 comes back. But then if there are bank charges, just like friction or something like this, then in order to go from 5 to 3 to 5, then you kind of need to make up for the money that you lost in the bank charges, right? So say 50 cents is lost each way. Then when you transfer $2, but this person's bank account only goes up by $1.50. And then in order to account for the bank charges in advance to make sure this person goes to 5, you need to transfer $2.50 here. So the work here is not going to be the same, basically because some money is leaking away. So in this sense, the loop test would fail for this, and so this would be, well, non-conservative money transfer, or in energy language, so it's non-conservative force. So we did that, and then if you look at gravitational potential energy, then we can define it just from the work formula. So remember that in general, the work is the integral force times force with distance. In the case of gravity, it's just a constant, so it's just mgh. But so the potential energy, it's got an extra minus sign here with respect to the work. So we have some relationship like this, and then the point that this slide is trying to make is that basically you can always set a zero point kind of arbitrarily. So you can just actually define gravitational potential energy like this with some kind of arbitrary 0 point of energy, and because you only really ever see kind of changes in the potential energy, or so basically you can only kind of observe a change in potential energy. You don't know sort of the absolute amount of potential energy ever really. So so you can just basically choose it by convention, right? So you don't have to, you can choose it according to your convenience. So it's often chosen such that the potential energy is just 0 when whatever axis you're using, the y value is 0. So, it might be like sea level is defined as 0. But that's a kind of an arbitrary choice. Okay, and similarly for elastic potential energy, you can also define it with an arbitrary 0 point, but usually again you define it as 0 when the spring is completely relaxed. Okay, and then I think this is where we got up to last time, which is kind of like the most important point in this whole chapter, which is the conservation of mechanical energy. So essentially, it's very simple. You just relate the work to, you relate the kinetic energy and the potential energy to each other because, one is kinetic energy change is work and potential energy change is negative work. So obviously, delta K is minus delta U. And then just from that, we can say that, for example, if you have, say this is the final kinetic energy and potential energy, and this is the initial, then basically the total amount of kinetic plus potential energy is conserved. Another way to just write this is simply to define the total mechanical energy. So we say we just consider the potential energy as a type of energy form, and you just sort of imagine it that you could either have it in kinetic or you can have it in potential, and it's perhaps it moves between the two, but the total amount of mechanical energy is the sum of those two. And then in that case, you're saying that the change in mechanical energy is equal to 0, because basically, if if one goes down, one goes up. So basically, that total amount is actually conserved. Okay. So I think probably, this is a relatively, intuitive concept, if you like. So, it's kind of in a, it's a kind of a commonly kind of known fact that sort of energy is conserved. So, okay. So you probably don't need me to give a money analogy in this case, but let's just for completeness, let's do it anyway. So basically, what we're saying here is that, okay, so for example, let's say there's sort of two accounts here, kinetic and potential energy, and maybe there's some transfer of $2 between these guys. Then basically, of course, before the transfer, the total amount, combined amount here is $9, but after the transfer, it's also $9 because this one just gave this one $2, so that of course this bank account goes down by 2, this one goes up by 2, so the total amount of money is still the same. So the total, this is a conservation of total money, and so it's the same, total is the same in each case, and same is true for energy. Okay, and so a physical example of this is, say, a pendulum. So if you have a pendulum, then so let me just draw the pendulum a bit bigger here so that you can see basically what's happening. So pendulum, here's the sort of the point that it's kind of fixed. So pendulum swings of course like this. And so let's look at 2 points here. So at this point here, the motion of the pendulum has stopped, right? So at this point, the kinetic energy is 0, but it has the maximum kind of potential energy. So we can set the 0 in terms of the height of this, say this is y. We can set the 0 of the potential energy to be here. So the gravitational potential energy is mg, y in this case. Then at this point, if this goes up to a height h, then the potential energy is just going to be mgh at this point. And then when it comes down here, so what's the potential energy here? Yeah, 0. Yeah. So just if you look at this, the y value is 0 here. So mg, we don't know what the mass is here, but it's just 0. And then the kinetic energy, what is this going to be? Right, yes, exactly, yes. So basically we can use our sort of conservation of energy, mechanical energy. So we know here that the total energy is mgh here, right? And essentially that energy has to be always conserved. So, in principle, to work out the kinetic energy, you'd have to know the velocity of the thing or the mass of the thing. So we might write half mv squared. But in this case, it sort of has to be equal to mgh here because energy should be conserved. And so we know that this plus this is equal to that, so in this case, the kinetic energy is also going to be mgh. So this is basically what a full cycle of the pendulum looks like. So this point on the left here is, it sees all potential energy, and then it starts to swing. This is sort of midway between this point and the middle. So this is where partially the potential energy is turned into kinetic energy. This is this point that we just talked about. And then, as it swings through, it gets converted. So basically, it's always shuttling back between potential and kinetic energy. Okay. All right, so let's do this question. So the figure shows 4 situations, one in which an initially stationary block is dropped and 3 in which the block's allowed to slide. Okay, so this is the one where it just, say, drops. This is where it goes down a slide. Right? And these are frictionless ramps. Rank the situations according to the kinetic energy of the block at point B. So here the B's like that. Greatest first. So which ones have the largest kinetic energy? Right, yes. So, yes, they are all the same. So, the reason why they're all the same is, of course, again, is conservation of energy. So, at A, these all have potential energy of, let's say, mgh, that, right? And then it goes down here, and we know that all that potential energy is reduced to the same amount, actually. So the remaining amount must be all in the kinetic energy. So, this is a kind of an interesting example because, like, if you did this from a force perspective, then, it's not entirely obvious that the energies should be the same, right? Because, for example, let's imagine a super shallow ramp, right? So if it's super shallow, then as this thing is sliding, this is going to actually, the force on it is actually much, much less, right? So if you imagine just dropping it, right, versus something with an extremely shallow ramp like this. So the force on this thing is going to be, so here's the normal force, this is mg. Sorry, it didn't draw it quite right. Mg is down, and this is the angle. This is whatever angle it is. So this is mg cos theta, and then so the force on this is mg sine theta. So if this theta is very small, then the force on this is very small, right? I mean, that makes sense. If you put a ball here and you just lift this up a tiny bit, it's not going to roll very fast, right? It's just going to slowly roll down, right? This will actually move pretty slowly at the beginning, right? But then the thing is that, the thing that's actually kind of different about these two is that, so with these two situations, what about the time that it takes to get from here to here? Are they the same? From this height to, say, this height? This keeps on going, by the way. Well, just you can think about it just intuitively. If this is like really shallow, compare that to just dropping it, right? Which is going to get to the same height down here faster. Yeah, just dropping it, right? So the thing about these two situations is that, okay, so this one is going to accelerate kind of much faster, right? This is going to go from here to just down very quickly. Whereas this one, if it's very shallow, it's going to like roll down really kind of pretty slowly, because this force is going to be pretty small, right? Sine theta is small, so there's small force acting on it, so it's not speeding up. But then, even though the force is smaller, it's going to roll down like a longer time. So imagine this one might be half a second. This might be rolling on this frictionless thing for like a minute, right? And then so even though the acceleration is pretty slow, it accumulates more and more speed, and then so by the time it gets down to the bottom, it's actually going at the same speed. And that's not completely obvious from a force perspective, because you might expect somehow, well, the time, these factors to kind of not exactly compensate, but basically they do. This is a small force but longer time. This is a larger force for a shorter time, and then basically these two kind of exactly compensate each other, and then you just always get the same speed at the end. So that's a kind of it's an interesting thing that from an energy perspective, you can just immediately just work out that they're going at the same speed down here, right? But then from a force perspective, you've got to do some calculations. You have to figure out the time that it's going to take, and then all this, and then work it out from that. And so you can see that actually, there's different ways of thinking about the same problem, and some make it like much, much easier than others. Okay. All right, so we've talked about how we can relate we can work out the potential energy change from the force. So we're sort of starting from the force, working out potential energy. Remember we did, mgh, or we had the half kx squared kind of formula. We started with the force, we integrated that, and then we got the potential energy. Now let's go the other way. So suppose we are given the potential energy first, and we didn't know what the force was, and we want to work that out. So we're going the other way. Now, so obviously, in the other way, the opposite of integration is differentiation. So if you have the potential energy, then what you do is you take the derivative of the with respect to the position. You were integrating with position, so we better differentiate with position. And then we need that minus sign again, because remember, delta U is equal to minus work, right? So this is how we get the force from the potential energy. So let's just check that it actually does work. So, say we're told that the gravitational potential energy is mgx, call it x here. Then taking the derivative of that, you get force is minus mg, and it's got a minus sign because gravity's down. Right? So that gives us the correct result. Say we're told the elastic potential energy is half kx squared, then we differentiate that, then we get forces minus kx, and that's Hooke's law. So of course it works. In terms of kind of graph, so the potential energy of these things, well, okay, maybe we should start with the force. So the spring is like half kx squared, so this is the force versus position. So it's like a straight line with a negative gradient, and gravity is just some constant, right? because the force is always constant, doesn't matter where you are, whether you're high or low, so long as you're not too high, away from Earth's gravitational field. So for the potential energy, if you plot it, then basically it looks kind of like this. So the spring looks like this parabola, and so it looks like parabola because essentially when you've got a spring, you squash it, it's gaining potential energy, or you stretch it, it's also gaining potential energy. So either way, you're going up. For gravity, it looks like a straight line like this because essentially it's just like the higher you are, the more potential energy you have. So if you're lower, basically you're going this way, lower you've got less potential energy, higher you got more. So you can see also graphically that the relationships are just a derivative here. So you take the derivative of this thing and then you end up with this. So that's just examples that we've already encountered. But what about the potential? Like you're given some potential energy curve that doesn't look so simple. So suppose you've got this potential energy curve that looks like this. How do we work out the force? Well, again, we take the derivative. Now, if this looks a little bit abstract and you'd prefer to have a more concrete example, you can think of this as a roller coaster, because potential energy is mgh, right? And in fact, roller coasters are a pretty good example of this because I think most roller coasters are not powered, right? They're just on wheels and then they just sort of roll down. Or at least the no, actually it probably depends on the type. Yeah, but you can get types where it's just basically rolling, right? And so the height is literally the potential energy up to some constant, right? Because basically the higher you are, the more potential energy you have. So when you just look at the roller coaster from the side, right? So it's on some track and it's doing this, then that is actually literally what the graph of the potential energy actually also looks like, up to a constant, which is this mgh. So if you multiply that height by the mg, then it's literally what the potential energy versus position graph looks like, right? So you can kind of, this is sort of an abstract view of potential energy, but if you want a concrete example, that's a good way to kind of think about it. So you've got a roller coaster track like this, it goes up and down. So if you're looking at what the forces are, then you can just take the derivative of this. And so, for example, here, where it's flat, or maybe at the end also, the potential energy is just a constant in that case. And so the force is actually 0. So here, that's why the force is 0 here. Over here, it's going down. So the derivative is negative. But then the relationship is the force is minus du dx. So it's the negative of the derivative. Yeah. So if you take the derivative here, it's a negative value, but with the extra minus sign, it's positive, so that's why it's positive here. Basically, what it's saying is that it's rolling down, so there's a force that has to be acting in the positive x direction. It's going to push you in the positive x direction. So clearly, as you roll down, you're going to be moving to the right here. Now, as you come back up here, there's going to be a point where the derivative is 0. So this is this point here. And then as it's coming up, that slope is positive. So the force has to be negative. So So it's actually slowing you down here. And over here, it's actually 0 again, so that's that point. Negative gradient, so it's a positive force. Here's a positive gradient, so it's a negative force. Yeah. So you can get the force relationship just by kind of reading the potential energy graph. And but using this conservation of energy idea, it's kind of you can easily read off what the potential and kinetic energy would be. So suppose you have a system where the energy is conserved, so it's conservative force. So then, say it has a total energy of E mech. Then what you can do is basically draw a horizontal line just to show that's the amount of energy that the system has. And because the potential energy plus the kinetic energy has to be equal to the mechanical energy, this actually gives you a very easy way of working out what the kinetic energy is, just simply by looking at the difference between this line and the potential energy here. So, for example, here, so what you might imagine this like a literal example would be that you have a ball here, and at that you're holding it there, and then just sort of let go, right? So obviously the ball is going to do something like it's going to roll down, roll up, roll down, and keep. Well, in this case it'll keep rolling to the right. So basically what you're doing there is you're supplying the ball with some initial potential energy, and the ball will roll down, and at various points, of course, so it'll be moving the fastest here, and then it'll slow down a bit as it comes up here, move faster again, slow down, move to the right there. So essentially this you can read off what the difference of this is, and essentially imply or infer the amount of certainly kinetic energy, but also the velocity. But because kinetic energy is half mv squared, you actually don't know which direction it's going. So from this graph, you can't really tell whether it's going left or right, because it's half mv squared, and either one will give you the same number, right? So from that, you sort of have to kind of imagine the thing moving and then figure out what the motion would be. It's basically because both situations are possible. So for example, here, say I started here and it rolls down, it'll basically keep on rolling to the right forever. But it's also possible that I started over here and then had some initial velocity that's the same velocity but moving to the left, right? In that case, what would happen is that it would roll this way, it would basically execute the whole thing, come back here, and then here is where it would stop, and then it would roll down, come back down, and then roll to the right. So basically both situations are always possible. So in the forward and the reverse legs, the velocities are completely reversed, obviously, right? But, I mean, basically both are possible. Just depends upon the initial configuration you had. Yeah, so this kind of, from this you can figure out whether a particle, some object, is going to be actually trapped or untrapped in the system. So just as I said there, in this case, this will just go flying to the right and then just never return back here because, well, unless there's something else over here blocking it. But basically, it's not really trapped in here. But if you have an energy, total energy that is less than, say, 4 joules in this case, then what would happen, for example, if it's 4 joules here, maybe a better example to start with is 3. So 3, it'll roll down here, come back here, come up to this point, perhaps roll down again, come up here. When it hits this point, it will actually roll down again and then come back here, and then now we're back to the start. And so basically it should roll back and forth between these two points forever. Started with 1 joule, then it would just keep on going back and forth just between these two regions here. For the 4 joules one, it would come back here and well, probably roll back here. So this is a little bit of a kind of a pathological example here, because you don't know if it will just stop here, or if it was just less than 4, then it would definitely roll down and keep on going back and forth. But if it's 4, it could just sort of sit there, right? So we can point out some of these equilibrium points. So, for example, these types of points where it's on a angle, this is not at equilibrium, clearly. Equilibrium meaning that if you just leave it there, it will just stay there. So clearly, if you just put it here, it would start rolling. This is what you might call stable equilibrium. This is what you call a neutral equilibrium, because this is particularly stable because essentially if you knock it a little bit, you'll actually still stay in this region, right? But if you knock this a bit, then it could just sort of slide forever. This is an unstable equilibrium because, essentially you're just sort of balancing it on the top of this hill here. A tiny force, which could come from anything, just like an air molecule hitting it or something, that could potentially make it start rolling it, and it would sort of feed back on itself, and it would just move away from that position unless you have it completely at the right position, and then make sure that there's absolutely no forces acting on it at all. Okay, does this make sense? Okay, all right, so then let's do this question. So figure gives potential energy function u of x for a system in which a particle is in one-dimensional motion. Rank the regions A, B, so this bit, BC, this bit, CD, according to the magnitude of the force on the particle greatest first. So this is magnitude of the force. So which one of these has the largest force?
CD, AB, BC.
Right, so CD and then AB and then BC, yes. Yeah, that's right. So force is the derivative, yeah? So it's a slope on the potential energy graph. And it says magnitude, so we don't really have to worry about the sign. So this has the sharpest slope, so it's got largest force. This is second largest. This is, in fact, 0, because it's constant. Okay, what is the direction of the force when the particle is in region AB? Right, yes. So it's positive. Yeah. So, well, calculationally, you can work it out like, okay, so the derivative of this is negative, and then the minus sign makes it positive, and then so that's why it's A. Sort of a mathematical way, but maybe it's good to also look at it from a physical perspective. So, with these potential energy graphs, as I said, you can just picture it like really like say a roller coaster or something like this, right? So you imagine a ball that is rolling along this landscape here. Now, obviously, it's going to roll down here, right? So if you put the ball here, it's obviously going to roll down. So that's in the positive direction. So that kind of confirms whatever we could do with confirms the formula. Right? Okay, good. Right. So, yeah, I saw this kind of interesting video that was talking about equilibrium points. Why don't we have a look at it? So this is obviously not really part of the course exactly, but makes a kind of an interesting point about equilibrium points.
That there's not a 3D object that currently exists that has less than 4 equilibrium points. For example, you can have this object here, which seems like it only has 1 equilibrium point. You can put it up top like this, and it rolls over and ends up stably upside like this. But this isn't just 1 equilibrium point. We have 1 stable equilibrium, 1 unstable here, 1 unstable here, and 1 unstable here. So that's 4 equilibrium points again. But one Hungarian mathematician named Gabor Demokos, who actually named this shape, the gambok, he tried to prove that this object can exist. And what he did is him and his wife collected a bunch of pebbles, and he just rolled them on the ground and saw how many stable and unstable equilibrium points they had, and saw if he could find any that had less than 4. And unfortunately, that failed. Eventually, though, they were mathematically able to find a shape that existed that had only 2 equilibrium points, 1 stable equilibrium and 1 unstable equilibrium point. The gambok is the world's first 3-dimensional convex and homogeneous shape that has only 1 stable and 1 unstable equilibrium point. So this is its stable equilibrium point, and this, of course, is its unstable equilibrium point. And there's no other stable or unstable equilibrium point on this whole object besides those 2. Now, you may have seen something that always pops up like that. There's toys that do this. But the cool thing about the gambok is that it's a homogeneous shape, meaning that it has the same density throughout the entire object. So basically, if you were to make an object that doesn't have the same density throughout it, for example, if I just put some weight on this tape roll here, this will easily always right itself. So it always comes back to this point. But in this case, you're cheating because you've made it a non-homogeneous shape. But in this case, there's no weights in this. The entire thing can be made out of a solid material, and it still behaves like this. Now, the coolest thing I think about the gambok is that you'll notice that this may look similar to something that you've seen in nature, a turtle. Most turtles right themselves just by wiggling their arms and legs and head around, and they can eventually flip themselves over if they get turned over. But some turtles have evolved the ability to flip themselves over using nothing but gravity. And basically what they've evolved is a turtle shell that looks like this. So if they get flipped over, no matter how they land, they can always right themselves if they just tuck everything in. Now there's only about 3 species of turtles that have evolved this way, but it's amazing that they've evolved this exact same shape that mathematicians had to prove existed. Now it turns out a true gumbuck is very hard to make, because if it has any minor imperfections in it, then it will create another unstable equilibrium point or even a stable equilibrium point. And that's why the mathematician had such a hard time finding any objects that, in nature that are true gumbucks. Even the turtle that I mentioned isn't a true gumbuck, but it's an imperfect one. Now these gumbucks that I have here are actually 3D printed. Hey everyone, thanks for watching another episode of the Action Lab. I hope you liked it, and I'll see you next time.
Okay. Yeah, so stop this. Okay. Yeah, so it's kind of quite interesting that you can have still kind of rather new kind of mathematics, even with this kind of these really old concepts of equilibrium points and so forth. So, okay, right, yeah, this is another aside that actually was sort of a question that a student asked in a class one time. So if you really view this whole thing as like a roller coaster, then you can easily derive the force to be something like this. So for example, if this is rolling, this is at some angle theta at this point here, then you can work out that the force is mg tan theta. Now, that's fair and good, but how do we actually get that relationship from a force perspective? It's actually kind of a bit sort of harder than you think. So, and basically this comes down to whether, what exactly this force that is being derived here is. So if you notice here, this is just a force that's actually in the x. Well, it's defined with only x variables, right? So the question that sort of arises: so which force are we exactly talking about when we derive this relation? So okay, easy enough sign. We just take the derivative and put a minus sign on. That's our force. But then, what force are we exactly talking about here? And so basically, because this thing doesn't really have any concept of anything in this sort of y direction. It's only talking really about something in the x direction. So you have to be actually pretty careful to work out what force that you should be kind of deriving. And what it sort of comes down to is, I think the only way that I could find to match up basically these two pictures is to firstly say look at what's the work done when you move this object by some small distance d along, say, this triangle here, and then work out basically what the force is based on this small movement, say, in the x direction. So this is kind of the only way that I could see to actually match up these two calculations. But yeah, it's actually surprisingly hard to actually work this force formula out actually from a kind of force perspective, because there's sort of multiple different forces, and so you really kind of need to be clear on what force you're talking about. I think basically the key thing here is that the force really has to be the effective force that you have to move this only in the x direction. So any force that's actually in this vertical direction shouldn't really actually matter. Okay, but anyway, this is a side, so maybe I won't go into that so much. So finally, we are going to look at the work done by an external force. So So up to now, basically, we've only considered kind of one force, and the role of that force was to transfer energy from one form to another. So, say in the gravitational potential energy example, basically that force was responsible to turn, say, kinetic energy into potential energy. In the case of the spring force was the one that was responsible, turning it again from kinetic to potential energy. But of course, there could be other forces, and if there's other forces, then they can also turn energy give one system, take basically energy from one system and give it to another. So this is what we're talking about with the external force. So suppose there's this block here, and it's being raised, say, by some height y. So obviously it has some potential energy. And say that is a rising vector because some girl here is picking up this box, right? So this is an external force that's not the force due to gravity, it's the force due to this girl. So that's it's a different force, right? So it's a different force. So for every force, there's some work, different work. So this work is going to be talking about the force due to gravity, but this force is due to this girl, and so there's a different work that's arising due to that force. So, she exerts some force F external, goes up by some distance d, right? Okay, so how do we kind of relate this to the things that we've been talking about? So, so if there's another different type of force, then we can view that as some kind of input into this system that we've been talking about. So essentially, we've been just talking about kind of two bank accounts, just the kinetic energy and potential energy of this object. Right? So say we're talking about some object with gravitational potential energy, then it's either potential energy or it's kinetic energy. Then now if something else sort of pumps energy into that, so you've got your system here, so say you can pick up that box, right? And then essentially now you are supplying some energy into that system. So then after you've pumped energy into that system, of course the total energy of that system is going to increase, right? Because you just sort of gave a bunch of energy to that system. So that will result in a change of mechanical energy of the system, mechanical energy being the total of the kinetic and potential energy. And that will kind of boost the whole energy of the system. So let's think of the money analogy again. So the work that we've been talking about previously is just converting between the potential energy and kinetic energy here, right? But of course, we can think of this whole thing as just one unit, and say there's a rich guy that gives a bunch of money to these guys. Everybody's bank accounts go up, so $10 goes to $14, $8 goes to $12. So basically the total energy, total amount of money of these two guys has now increased. Now that doesn't stop these guys transferring energy or transferring money between them. They can still do that. So perhaps this $14 here is partially due to this guy giving this guy this potential energy money, partially due to some exchange here, but nevertheless, whatever process happened of work between the potential energy, if you look at the total here, it's gone from $18 to $26, so rich guys given these guys $8, obviously. So this is basically what we're talking about with the external work. So it's not only possible for some exchange to be happening, but it's also possible that there's an injection of energy from somewhere else that boosts the kinetic and potential energies. Yeah, so example would be throwing some bowling ball, say. So say it's initially on the ground here, so the potential and kinetic energy is 0. Now you come along here, pick it up, then the moment you pick it up, you basically already given it some potential energy, right? So you've gone from 0, 0 to some U0, still the kinetic energy is 0, and then say you go and now throw it, now you just gave it also kinetic energy. So you've given it both potential energy and kinetic energy. Firstly by lifting it, and then secondly by throwing it. Okay. So now let's consider this example. So if we include friction into the picture, then this actually gives a kind of yet another bank account, if you like. So we had kinetic energy, we had potential energy, and then there's actually also kind of thermal energy, right? So actually you can keep on going with this whole thing where you essentially have different bank accounts accounting for different forms of energies. So, for example, if you have this block here and has initially some velocity v0, you pull it with some force, finally the velocity changes to some other value, but actually during that whole motion there was also friction. So friction is acting in the opposite direction. So in terms of we can work out actually what the change in the kinetic energy is actually. So for example here, we can use Newton's laws to say that, okay, here's my force F, but then the frictional force was kind of negative. So that is going to create some acceleration, which is equal to that, right? So F minus Fk is equal to ma. Okay, so maybe we should redraw this so that we've got a force here, frictional force like this. So the first statement is that F minus Fk is equal to ma, so this thing has mass m. And so we can use our formula v squared equals, okay, let's use the same notation, sorry. V initial plus 2a, and we're going to move it through some distance d here, right? So this is our acceleration here. So let's put this one, so in other words, this means that acceleration is equal to F minus Fk divided by m. So let's put that a into here. we can just rearrange this a bit. So let's just multiply this thing by m over 2 throughout. So it's half mvf squared is equal to half mvi squared plus f minus fk d. So you can see that, well, we can put this on the other side, and then basically what this is going to end up saying is that this is the change in kinetic energy is equal to F minus kd. Let's just multiply that out. Force times distance minus friction force times distance. And so we can kind of associate a couple of different values to this. So this thing is the work that you did, right? So you were the one that was pulling this thing. You know, you could feel that frictional force there. And so this is the work that you did, in other words, the external force, right? So we can rearrange this thing. So Fd, which is the external force, going to be equal to the change in kinetic energy plus Fk d. So we can so change in kinetic energy. In this case, there's no potential energy change, so this is why they wrote it as change in mechanical energy. But this thing here, this FKD, is actually the, you can say this is like a change in the thermal energy this time. So friction eventually, when you're dragging something along here, you know, that energy eventually goes into sort of heating up this table, right? So what's happened here is, you know, that force that I used to move this pen across the table is kind of heating up the pen and the table, right, eventually. So that's where all that energy goes. So in that case, basically the thermal energy has now changed. So we can kind of think of it like yet another bank account. So we're talking about, you know, bank accounts of only potential and kinetic energy, but in this case we'd have like a third one. It'd be a thermal energy bank account. So the work that you did goes into basically increasing the thermal energy of the object, plus also speeding up the object, which is presumably the aim of whatever you were trying to do in the first place. Yeah. Okay. It's working. All right, so let's try this question. So this figure shows three situations showing a plane that is not frictionless. And a block sliding along the plane. Block begins with the same speed in all three situations and slides until the kinetic frictional force has stopped it. Rank the situations according to the increase in thermal energy due to the sliding, greatest first. Oh, yeah, sorry. Yeah.
I have a question.
Mm-hmm.
Where is the external force?
I think in this case, there isn't any. Because it is just given some initial energy, So yeah, this is a good point. This is a great place to start actually with this question. So in the previous example, like here, I was actually pulling on it with something, so dragging it through. But in this case, I think it's just given some initial velocity, and it just slides. Yeah. So I think W external is actually 0 in this case. So perhaps might help. So in the previous example, there was no change in potential energy, but then the way that it was written was like this. Okay, so just intuitively, which one do you think would cause the block to heat up the most? Yeah, number 2, yes, that's right. Yeah, just intuitively, I mean, just imagine, like, I don't know, it's a good example. You're on one of those sleds or something, right? Not on snow because you don't notice the heat, but say in summer you're on some sled and you're sliding down something. Obviously, if you're sliding down something, you're going to generate a lot of friction, right? So number 2 is going to be the one that should be heating up this block the most. Okay, so how do we kind of relate that to whatever we've been doing? So I think what we do is we start with the equation that we were given. So this is our change in mechanical, this is change in thermal. So we already said that external work is 0. Change in mechanical is actually change in kinetic and change in potential. And this is the change in thermal. So what is the change in kinetic energy for all these cases?
They'll stop with the inertia.
Yes, that's right, yeah. They all start with the same velocity and they all stop, right? In other words, the final velocity. So, yeah, so basically the point is that this is the same for all 3 cases, right? So there's actually no difference between all these 3 cases. And so if we just rearrange this equation, so this is Kf minus Ki, so it's got minus sign, so it's K initial minus Kf. Well, maybe we can write this one also. Uf minus Ui. Kf is 0. Ki is the same, so we don't know what it is, but it's the same. So we can just call it K0. And then we've got Uf minus Ui. This is the change in potential. So the potential energy is definitely changing. So basically this thing would be saying, well, this one would be the biggest for the cases where the change in potential energy would be what, negative or positive? This is delta. So if we want this one to be big, obviously we want initial kinetic energy to be big. Makes sense. This one, do we want it to be negative or positive if we want this to be big?
Negative.
Yeah, negative, right? Yeah, because it's got a minus sign. So this thing has to be negative, yeah. So basically, if there's a change in potential energy that's negative, then this thing is going to end up being big. So it actually matches our intuition. Number two, this is a case where I don't know, batteries apparently. So this is a case where the potential energy is going down. So this thing is going to be negative. 3 is a case where the potential energy actually increases. So this is actually going to be the smallest case. And in 1, the change in potential energy is 0 actually. So this is sort of in the middle. Yep. Okay. All right. So we'll leave it there. Okay. And yeah, so if you could just leave your homeworks at the front, and I'll see you on Thursday.